Hello, this is Questionable Coding with Vladimir, and we are starting to discuss essential algorithms. It's a new series of videos on my channel where we'll discuss most important algorithms that you really must know before you approach an interview. And we'll start with one of my favorite algorithms called binary search. I think you all heard of it, but still there are a lot of tiny details, and you stumble upon binary search when you start, when you continue doing algorithms, because it's all over the place. There can be very small and easy tasks when you need to implement the search itself. It can be a modification of binary search when you have some constraints, maybe an rotated array instead of just a simple sorted one. And there are a lot of big tasks that have as part of them, they have binary search to improve efficiency, and you need to develop a skill to spot where you can use binary search, how you can reduce your task to use binary search. So I highly recommend to learn it and learn the implementation almost by heart, because you will have to reproduce it many times, and sometimes it won't be the hardest part of the task. So binary search, sometimes called logarithmic search, because it's very closely related to log n runtime complexity, and we'll see why. Sometimes it's called, I think it's called binary chop, and that's basically the concept. You should have some sorted array. It can be a tree, but it's a bit of a different thing that we also cover at binary search tree. It's a data structure which uses this binary search concept, but usually it's a sorted array. You need to make assumptions on which part of the array fits you. You need to have it sorted, otherwise you won't have this way of assuming which part is good and which is not. So on every step of our search, we will divide our array into halves, and we will decide, depending on a given value that we search, we will decide in which part of an array we should search for a value. Just to give you an idea how efficient it is, how efficient the log n logarithmic runtime complexity, imagine a data set, an array of 1 billion elements. So to find one element in this sorted array, we need no more than 30 steps. And I'll explain why it's so efficient. So I think we can start. Okay, let's do this manual task when we have an array, and it's ascending array. You have values here, they are covered by question marks, so we don't know real values. That's how algorithm works. So up front, we don't know values in the array, we need to find some value. That's why we need somehow to compare those values to the value that we're searching for. And one way to do it is to do just a linear search. It means we'll go from left to right, and I'll uncover some values. So it will be 1, and let's say we're searching for 12. And then it will be 3, and then it will be 4, and in the worst case, we'll go to the very end. And it will give us big O of n. So it's a linear search. But we don't want that, we want to improve that, and we have a tip here that array is sorted, and it's ascending. It means that the first value and all other values, they ascending. Yeah, they are ascending, and the last one will be the biggest value. So let's hide them. And also we have indexes. We know about indexes. If we have an array of lengths 15, we'll have indexes from 0 to 14, because they are 0-based and length is not 0-based. And it will help us to navigate through an array. So what do we need to do to improve our search from linear to something else? And this something else will be logarithmic complexity. And that's much better. And we'll talk about that a little bit later. But what we have right now, we have a number that we're searching for. It will be 12. It doesn't matter much, but I think it will represent our idea in a good way. And we have two pointers. One pointer is pointing at index 0, and one pointer right is pointing to the last index. In this case, it's 14. So what we need to do first, we need to understand the middle between those two indexes. And that will be basically 0 plus 14 divided by 2, and it will be 7. You may ask what will happen if there will be one more element and it will be like 7.5. Then we can round it to 7 or to 8. It depends on our implementation. Both options will work, but you should be consistent and round only to a lower value or to higher value. Okay, well, we pointed out that our center is 7. What we're going to do right now, we're going to uncover the value, so we'll compare this value to 12. So the value is 48. What can we do from this point? We know that we have 48 in the middle, and our value 12 is less than 48. And we have an ascending array. It means that everything to the right will be more than 48. And our value is less than 48. It means that we are not interested in this entire part, and we can throw it away. And for that, I prepared this kind of graphics. So we just eliminate all those options. So half of the options are gone. What we need to do right now is drag our pointer, and now it points to 6. Now we just repeat the same procedure. We have left pointer and right pointer, and we need to find something in between. And it will be 0 plus 6 divided by 2, and it will be 3, this index. So let's check if this value equals 12. 8, it doesn't equal 12, and it's less than 12. And we know the array is ascending, that's why our 12, our value, should be in this quadrant. That's why we eliminate the left one, including 8, because we already invalidated it. So we're doing the same, we are just excluding it, and we are moving the left pointer now, because our value was not to the left, but to the right. And we have left, which is equal to 4, and right pointer equals to index 6. Now we need to find something in between, and this will be 5. So let's uncover the value, and it's 14. It's more than 12. We're doing the same thing. We're eliminating everything to the right. Everything to the right. And now we move our right pointer to the same pointer as the left one, because we have no other pointers there. And we're checking the last index. And here we have 12. Now we found the value. So we're just finishing the script. The value is there. If the value would be smaller, for example, then we would give, or for example, bigger, we would move the right pointer, and we would stop. When the right pointer is to the left of the left, then it means that something wrong is going on, and we should stop. It will be in our while loop. So I hope it gives some idea on how the binary search works in a standard array. Usually when we talk about binary search, we're talking about a sorted list. But also, I think you've heard about binary search tree. It's different. It's a tree data structure which uses the same idea as we used for binary search in an array. So let's create, having this sorted array from the previous example, let's build a binary search tree from it. And we'll see what properties are there for a binary search tree. I won't draw edges between parents and children, between nodes, but I'll do it in the very end. So first of all, we're also picking the middle element. It will be 48. I think you remember it from the last example. Then we have two parts left. Everything that's to the left of 48, everything to the right, which is bigger than 48. And we are picking middles for both sides. So from the left we pick 8, and from the right we pick 72. So these two will be children of 48. And we have four parts left. And for each part, we are also picking the middle element. For this one, it will be 3. For this one, it will be 14. This one, it will be 54. For this one, it will be 79. So we see now we have a binary search tree. So for every node, we can apply a rule. It's already there, that everything to the right of the node is bigger than this node. Everything to the left of the node is smaller than the node. And the same can be applied for this node, and for this node, and for this one. You see, 79. Everything, every child that to the left of 79 is less than 79. Everything to the right is more than 79. So when we start from the root, if we want to find some number, let's say 77, we check if this number is bigger than root. If it's bigger, then we eliminate this part to the left, including the root itself, and we continue with 72. And we check if 77 is more or less than 72. It's more, then we are also removing this part, because the value should be to the right. And now we check 79. 79 is bigger than 77. Then we are eliminating everything to the right and moving to the left child. And the left child will be 77. That's what we are searching for. So it works the same way as for an array, but using this tree logic. Another important question, and don't be surprised by a lot of numbers, they are quite simple, we'll look at them in details. So when we talk about binary search tree, sometimes people ask, why is it logarithm of n, log n, complexity? So at first, let's see how the power of 2 works. So 2 to the power of x will equal b. If the power is 2, then b will be 4. If the power is 3, it will be 8. I think you know it, but let's follow it to bigger values. If it's 9, then it will be 512. If it's 10, it will be 1000. If it's 20, it will be 1 million. If it will be 21, we will double the million. And if it will be 2 to the power of 30, it will be 1 billion. By the way, it's quite easy to follow. You have power of 10, it will be 1000. Power of 20, it will be 1 million. And power of 30 will be 1 billion. So it's increasing. It is pretty easy to remember. But okay, what we have here is that every step, every power that we get, we just multiply our previous value by 2. And we have logarithm, which means if we have a logarithm of base 2, and it's the default one in this informational technology area, I would say. So if it's 2, we can even remove it. So it will be the same as I have in title, just log n. But let's keep it for now. So if we have log base 2 of b, it will equal x. So we can see that they are very much related. It's basically the same thing. So if we have logarithm of base 2 of the number 4, it will be 2. Of the number 8, it will be 3. Sorry for this strange selection. If it will be number of logarithm base 2 of 512, it will be 9. The same thing we had here. We had the power of 9. And for 1000, it will be 10. And for 1 billion, it will be 30. And it helps us a lot. So every time we made one step forward in our logic, when we excluded another half of our array or our tree, we decreased our possible options by 2. We divided them by 2. So if we had 2 million options, in one step we decreased it to 1 million. And it's super cool. It means that if we have 1 billion options like we have here, we can find, in the worst case, we can find the value we need in 30 steps, which is insane. So our number is growing like crazy, exponentially. The next step, it will be 2 billions, and we can find the exact number in 31 steps. And that's how we have this logarithmic runtime complexity, which is extremely efficient. The more efficient will be a constant runtime complexity, but it's something superb. It's like a hash map lookup. But for the search, binary search works perfectly. The only thing that we need our array to be sorted. Otherwise, we'll spend too much time on sorting it. So usually when you hear about sorted array, you should think of a binary search. If you think that the complexity can be improved to logarithm log n, then you better start thinking about the binary search and how to apply it. Let's now code the binary search. We'll create a function we'll call binary search, and there will be two values. First of all, array, and it's our haystack, and there will be a value that we'll be looking for. And first of all, we'll create pointers. We'll call it very simple, left and right. So left will be equal 0 and right will be equal to array length -1. It's pretty important, so don't miss this -1. It can be tricky. Now we'll have a while loop, and it will be left less or equal right. When right will be to the left of the left, then something goes wrong and we will stop. The next thing, I think it's one of the hardest things in binary search, is to calculate this middle index. So let's call it middle. Let's call it just middle, because we have left, right, and simply middle. And it will be left plus right minus left divided by 2, and we're getting the mass floor of it. That may look pretty strange, because that's not the easiest way to find the middle element. So we'll put a check mark here so I could describe what's the logic behind that. And the next thing that we're going to do, we're going to check if our middle element, which will be our middle, is equal to our value. If it is, we will just return true. Let's just return if the element is there or not. If it doesn't equal, then we need to decide. If our value is more than our middle, then we'll go to the right. And for that, we need to reassign the left pointer, and it will be middle plus 1. So we're ignoring everything to the left of the middle and the middle itself. If our value is to the left of the middle, then we need to reassign the right pointer, and it will be middle minus 1. In both cases, the second pointer, in this case the pointer right, will remain the same, and in this case pointer left will remain the same. And if we reached our condition and we couldn't find the value, then we'll return false. Now let's understand why this part is better than the more simpler one. So the simpler implementation will be like this. It will be mass floor of left plus right divided by 2. So it looks better, much simpler than this one on the top. But the problem is, when we have a sum of left and right, it can cause an overflow. So left can be very big and right can be very big, and they can exceed our maximum integer. That's why instead of doing that, we are finding a difference between right and left. We already not exceeding the right value, so we will never be more than we currently have to the right. So we are safe. Then we divide this result by 2. And then we add this half of that interval to our left value. And that's how we get the middle between left and right without summing up left and right and getting huge numbers, potentially huge numbers. So I think it's all the basics that we need to know about binary search. There are much more things about that. There are many hard tasks that include binary search when we do it in a rotated array, when we have a lot of similar numbers or same numbers and we need to find the leftmost number, the rightmost number. So there is a huge variety of tasks with binary search, and usually you will face at least once during your interviews, you will face some task that includes binary search. So please learn it by heart, understand it in a best way possible, and it will help you a lot. So stay tuned, please subscribe if you didn't do that, and we'll have more essential algorithm in this series. I think it will be interesting. Stay tuned.